Hello everyone, we are Team Celestial from the Manipal Institute of Technology, May HU. Our team member is Muhir Kapoor and is thrilled to present our project on developing a space settlement at the Earth-Moon L5 point, utilizing Earth's space elevator. Imagine a thriving community of 20,000 residents living in harmony across 4 cylinders, each home to 5,000 individuals. These counter-rotating cylinders, with a radius of 260.5 meters and a length of 338 meters, are designed to negate gyroscopic effects and rotational instabilities, ensuring a stable and comfortable environment. Radiators are located on the end caps, and strategically placed windows offer natural sunlight and breathtaking views of Earth and the Moon. Inside these residential cylinders, you'll find concentric internal shells housing everything from warehouses and research areas to recreational spaces, industrial facilities, commercial zones, and agricultural areas. 2 non-rotating cylinders will serve as ports, equipped with extensive maintenance and repair capabilities for spacecrafts. The sun-facing side of these cylinders will be adorned with solar panels, while the backside will feature radiators and windows, supporting zero-gravity research, manufacturing, and recreational activities. Artificial gravity of 1 g will be achieved at the cylinder surfaces with a gentle rotation rate of just under 2 rpm. Residential areas will be pressurized at 0.75 atmospheres to reduce stress on the walls of the settlement, while warehouses and transport tubes will remain unpressurized to ease the commute of cargo. Let's dive into the material configuration of our space settlement hull. The outermost layer is a mesh of 1 mm thick graphene superlaminate, providing extreme tensile strength, helping it withstand extreme centrifugal forces. Next, hybrid Whipple shields with an aluminum honeycomb core are used for protection against micrometeoroids. A fiber-reinforced aerogel layer integrated into MLI ensures thermal insulation, while a polyethylene boron composite shields against cosmic rays and solar radiation. Aluminum 6061-T 6 panels provide structural integrity, and an additional thin self-healing ionomer-elastomer layer heals any cracks on the panels. The design features advanced windows made of boron nitrogen, nanotube-reinforced fused silica that offer exceptional strength and radiation shielding, while nitrogen is integrated to provide thermal insulation and mitigate crack propagation, complemented by anti-UV films. Sunlight is regulated through an electrochromic glass layer, allowing dynamic control of light penetration. Additionally, repurposed cargo containers are creatively adapted for use as homes, buildings, and vehicles, enhancing the structure's versatility. Concentric inner shells are built with fireproof geopolymer concrete, reinforced with high-tensile fibers, ensuring both durability and safety. Our space settlement's primary power source will be a solar power satellite, positioned in the same orbit as the settlement, beaming 215 megawatts of power to a 500-meter-wide rectenna. As a secondary source, radiation-hardened perovskite solar panels with up to 30% efficiency will be placed on the rotating hulls and sun-facing sides of non-rotating cylinders, generating an additional 215 megawatts. For backup power, hydrogen fuel cells will be used. Power will be allocated as follows: 40 megawatts for residential use, 120 megawatts for agriculture, 65 megawatts for operations, 215 megawatts for industrial activities. The system incorporates innovative power transfer through roll rings that bridge rotating and non-rotating surfaces, ensuring seamless energy transmission. It utilizes a smart electrical grid alongside SCADA systems for efficient power management, optimizing distribution and control. Additionally, graphene-enhanced loop heat pipes are employed to dissipate waste heat by transferring it to radiators or repurposing it for industrial applications. The atmosphere will have the following composition, keeping in mind the 0.75 atm pressurization: 70.15%, nitrogen 28%, oxygen 1.75%, water vapor 0.1%, CO2 enhanced in agricultural zones to boost crop yield. HVAC systems will maintain optimal temperature and humidity, ensuring a stable and comfortable environment. Landfills will be located in the agriculture and utility shell, away from cities for human comfort. A closed-loop bioregenerative system will recycle water, nutrients, and waste. This system employs a photobioreactor to produce oxygen and absorb CO2, an anaerobic digester to break down organic waste into essential minerals, a nitrification chamber for nutrient conversion, and a water purification unit using microbial desalination cells and urease-producing bacteria. Over 1.7 million square meters will be dedicated to agriculture and utilities. Vertical aeroponic farms will produce crops, genetically engineered yeast will be used for dairy production, and meat and seafood will be grown in bioreactors. Crops will include citrus fruits, vegetables, grains, and nutrient-rich meats, acting as countermeasures to radiation exposure. For psychological well-being, green walls and indoor gardens will be present. Our settlement will be a hub of various industrial and research endeavors, acting as a staging area for deep space and cislunar missions, providing spacecraft maintenance and repair. Zero-gravity manufacturing will unlock new materials and production techniques, producing defect-free crystals for advanced electronics, ultra-pure alloys for high-performance engineering, and ZBLAN optical fibers for lossless data transmission. Microgravity research will push the boundaries of science and medicine, enabling advancements in material science, regenerative medicine, and pharmaceuticals. Recreation in our settlement will be designed around low and zero-gravity experiences that are impossible on Earth, including 3D obstacle courses, aerial gymnastics arenas, and low-G water sports. Factoring in the above calculations with miscellaneous costs of robotic systems, thrusters, etc., the settlement is expected to have a total mass of 6.8 billion kilograms, transporting 6.8 billion kilograms to the Earth-Moon. L5 point is a massive challenge. Let's compare two methods, rockets and space elevators. Rockets with capacities to ship 30 tons per launch to geostationary transfer orbit would require up to 226,667 launches with a staggering cost of $51.98 trillion USD, taking 227 years to complete the job. In contrast, space elevators have a cost of $500 per kilogram, making the total mission cost $3.4 trillion, and completing the job in just 40 years. Space elevators generate zero emissions, making them a more sustainable and efficient long-term solution for large-scale space transport. Cargo deployment from the apex anchor takes full advantage of Earth's rotational velocity, 7.76 kilometers per second, allowing for releases without any extra fuel needed for interplanetary missions. This high-velocity release enables rapid travel times, such as reaching the Earth-Moon L5 point, 384,400 kilometers away, in just 5 days with an optimized trajectory. Complex modules or machinery that cannot be assembled by autonomous robots at Earth-Moon L5 will be assembled and launched at the apex anchor. Many space settlement designs propose using a lunar mass driver to transport construction materials. However, relying solely on a mass driver presents several challenges. First, deploying such a system via rockets is extremely costly, not only because of the expense of rocket launches, but also due to the mass driver's significant weight of approximately 424,800 kilograms. Second, even if bulk raw materials were efficiently transported from the Moon, a variety of highly specialized and complex components would still need to be launched from Earth, further escalating costs. Ethan J. Muller's study highlights that a lunar mass driver could deliver up to 100,000 tons of material annually to the Earth-Moon L5 point. Yet, without addressing the challenge of transporting essential equipment from Earth, the mass driver alone would be insufficient for constructing a sustainable settlement. This is where the integration of space elevators with mass drivers becomes transformative. By combining these two technologies, we can streamline construction and logistics significantly. The mass driver would efficiently transport lunar regolith for structural purposes, while the space elevator would handle the delivery of critical components and equipment from Earth. The amount of lunar regolith to be transported is as shown. This synergy could reduce the overall material delivery timeline from 40 years to just 26 years, as the space elevator would need to transport only 4.4 billion kilograms of specialized mass. Furthermore, the mass driver would establish a continuous supply of lunar ores and resources, supporting ongoing research, processing, and manufacturing activities. Together, these integrated technologies not only address the inherent drawbacks of a standalone mass driver, but also pave the way for a more efficient, sustainable, and cost-effective approach to space settlement construction and long-term colonization. Space elevators are crucial for the success of this project. They offer a sustainable and efficient solution for transporting the massive 6.8 billion kilograms of materials needed for the settlement. Compared to rockets, space elevators are significantly more cost-effective and environmentally friendly. They can complete the transportation in just 40 years at a fraction of the cost, making them indispensable for large-scale space construction. By integrating space elevators with lunar mass drivers, the project can further streamline logistics, reducing the overall material delivery timeline to 26 years. This synergy ensures a continuous supply of resources and supports ongoing research and manufacturing activities, paving the way for a sustainable and cost-effective approach to space settlement construction and long-term colonization.